at this point, I'd like to remind you that the same substrates usually that can go through elimination can also go through substitution. Most substrates are equally good candidates for substitution, and most bases are also good nucleophiles. So the same alkyl halide that we previously showed the elimination for, the same alkyl halide when attacked by a base goes through an elimination, and when attacked by a nucleophile can also go through a substitution reaction where all that happens is the nucleophile takes the place of the leaving group. When we do synthesis questions, and the way you need to, you could be tested on this knowledge that the same substrate can go through both substitution and elimination. How do you choose conditions that favor one over the other? That knowledge could be tested two ways. One way would be given a set of conditions, given a substrate and a particular base or nucleophile, and a set of conditions, you need to determine the product. And you need to know what those conditions are. Given certain conditions, what product is most likely to be made. And going backwards, you could also be given a product to make, for example an alkene, and you need to choose the suitable conditions and the reagents and starting materials to make that alkene that will prevent or minimize substitution. So which brings us to the point previously we have discussed about elimination conditions that favor elimination. And here I want to give you a minute to think back to, based on what we have learned so far, what mechanism do you remember is best for elimination, for creating alkenes? E1 or E2? And what substrate? And what base? Let's think about them one by one. So what's the mechanism that's most suited for E1, for elimination? Is it E1 or is it E2? Is there a preference? And the answer is yes, E2. Because E1 generally has more competing reactions. So E2 is better suited to make alkenes. What about the substrate? What do you think, what substrate is best suited for elimination? And the answer is tertiary substrates are the best suited for E2, because now that we've decided that E2 is better, tertiary substrates are the best for E2. The reason being that, well, because usually substitution and elimination are competing reactions, E1 competes with SN1, but we're trying to make E2 happen. E2 competes with SN2. Choosing a tertiary substrate minimizes SN2 because they're the least suited for SN2 reactions, and it forces E2. And then the last thing that we mentioned, and a really important point to keep in mind, is the choice of base. What base can we choose that can favor elimination over substitution? And the answer was preferably strong, bulky base. And the reason for that was strong, bulky bases are usually poor. Bulky bases are usually poor nucleophiles. And if we have a base that's a good base but a poor nucleophile, that's also one where we can minimize elimination. So here are your conditions that will favor, again, that will favor elimination over substitution. We said E2 is better. E1 usually has more competing reactions. Tertiary substrates are the best. And strong, bulky base. And this point is especially more important when the substrate is not secondary, when the substrate is not tertiary. For example, a tertiary alkyl halide or any tertiary substrate. Those are the most difficult to predict, the reactions, and that's when, so if you have a secondary substrate, when you have the leaving group coming from a secondary substrate, That's where the choice of base, a strong bulky base, is even more critical. The part we need strong because strong favors a second order reaction. Strong makes E2. Strong forces the reaction in the E2 pathway instead of the E1. And the bulkiness prevents SN2 from happening or minimizes SN2. Because bulky bases are usually poor nucleophiles. And the most important thing that I want to add to this point is a strong bulky base also facilitates the making of a Hoffman product, which is also called the anti-Zaitsev product. So we have learned previously that most eliminations follow the Zaitsev rule and form the Zaitsev product, which we can review. Go back to one of the clips that discusses that. But the Zaitsev product basically is the most substituted product in elimination, meaning if two alkenes can be made from an elimination, because some substrates can be eliminated two ways at two different sites to give two different alkenes, the more substituted alkene is the one generally formed, which is what the Zaitsev product is. That's what the Zaitsev rule is. And the least substituted alkene is the Hoffman product. So for example, if we have this alkyl halide, which when treated with the ethoxide ion, which is a strong base, but it's non-bulky, we expect the Zaitsev product to form. So this product, the major product, will be the Zaitsev product. Another alkene that can be formed here, when this alkyl halide goes through elimination, when treated with a strong bulky base like tertiary makes the Hoffman product in greater yield. So if for this is helpful when predicting, if you're given a question like this, where you have an alkyl halide and you have given a substrate and you need to determine the product that will result from an alkyl halide reacting with a substrate, that now you know when you have a non-bulky base, the Zaitsev product is favored, and that's the product that's the product you should indicate as your major product. And when you have an alkyl halide that's treated with a strong bulky base, if you're asked for the product, you should have the Hoffman product as the major product, the least substituted alkene. Now the situation is if the situation is reversed, when you're given the task of creating an alkene, when you have to synthesize an alkene that's the most substituted, you go for a regular non-bulky base, strong base. When you have the task of synthesizing the least substituted alkene or a Hoffman product, then you choose a strong bulky base as your choice of base to synthesize your Hoffman alkene. And the reason for that is when a base itself is bulky, it prefers to attack the hydrogen, abstract the hydrogen from the position that leads to the formation of the least substituted alkene. And here's another example. This is a tertiary alkyl halide, tertiary substrate, and this is the carbon that has the halogen attached. Now the double bond could form in one of these locations which are equal, or a double bond could form here, depending on if one of these hydrogens is removed or one of these hydrogens is removed. So we have various beta carbons in this case, and one of the products results if one of these hydrogens is removed is a terminal double bond. which is di-substituted, and that would be the Hoffman product. The other product that results from the elimination of this alkyl halide would be if the double bond is made between these two carbons, if one of these hydrogens is removed, and that would be the Zaitsev product. It would be a tetra-substituted. It's an internal alkene. It's not a tri-substituted alkene. So we can already see this is more stable because it has more substitution around the double bond. And depending on the reagent, the base that you treat this with, you will get either the Hoffman product or Zaitsev product as the major product. And if you're given the task of making this, you would choose the appropriate base depending on which alkene you want to be your major product. If you have any more questions about this, the reason I mentioned this at this point was when we were talking about conditions that favor elimination, and we mentioned the use of bulky bases. So now there's two. The choosing a bulky base serves two purposes. It minimizes SN2 and favors elimination, and also it's useful when we're in need of making a Hoffman product, least substituted alkene of an elimination. If you have any more questions about this, if you'd like any more detail on this concept, you could ask me questions. Based on all that we learned, all the conditions that we learned, I expect you to be able to predict the product, the major product, or the major reaction given a set of conditions, given the substrate and the base. And I also expect you to think backwards, and when given the task of making an alkene, choose the appropriate conditions. So let's try a few problems. This one is actually problem 7.13 in the Weight Organic Chemistry book. Part A says, the problem says to predict the major product. So it reads, for each reaction decide whether substitution or elimination or both is possible and predict the products you expect. Label the major products. So the first part A says it's 1-bromo, 1-methylcyclohexane in NaOH and acetone. Well, the first thing would be to draw that, and before looking at the answer, I would like you to take a minute to predict the products, to decide if substitution can happen, if elimination can happen, if both can happen, or which one will be the dominant major product. That's the right structure, 1-bromo, 1-methylcyclohexane. This requires you to be able to go from given a name, to be able to draw the right structure. Once you have the right structure, the first thing that you should notice, it's a good idea to pause here at this point and try to answer this question, and then then you might want to see the explanation. So the first thing when you draw this product that you should ask yourself is what kind of a substrate do you have? Well, this is a tertiary substrate, a third degree. And so of all the options, and this is a strong base, then you ask yourself what kind of a base you have. You have a strong base / nucleophile, which is going to favor SN2, second order, SN2 or E2. It's going to favor second order reactions. Well, because we have a tertiary alkyl halide, we have a tertiary substrate, SN2 is not possible. So here we had decided based on the base strand that SN2 and E2 are both possibilities, but SN2 is not possible. That leaves E2 only, which means this elimination will be the major reaction, and the products would be let's see. Well, this is the carbon that's losing the Br, and the double bond could form here between one of these carbons, which are going to turn out to be equal, or the double bond could form there. So one of the elimination products would be and this is the Hoffman product because it's the least substituted alkene from the products. The other product would be if an elimination occurs here, one of those hydrogens is removed, and that's the Zaitsev product. And how do we know which one's major? Well, in this case, we have a non-bulky base. We have an unhindered non-bulky base, so the Zaitsev rule applies, and this will be the major product. Now, part B tells us to try the same molecule. It says 1-bromo 1-methyl cyclohexane in triethylamine. Or you could write it like ET3N. Now, in one of the clips, I've mentioned the strong bulky bases that favor elimination that are hindered, that prevent or minimize substitution, and lead to the Hoffman product. And triethylamine is on your list of those bulky bases. So as soon as we see that, we already know that our substrate is a third degree, which tells us that it's not, SN2 is not a possibility. And triethylamine is bulky base, which will, when you have both products that are able to go through that result from the elimination, depending on which hydrogens are lost. In this case, the opposite is true. Because we're dealing with a hindered bulky base, it leads to the Hoffman product in a greater amount. This will be the major product in this case. This was the answer to B. Because the triethylamine, being a hindered bulky base, will abstract a proton from a location that will lead to the formation of the least substituted alkene. In C, we're asked to predict whether substitution, elimination, or both can happen for chlorocyclohexane in NaOCH3. Sorry, chlorocyclohexane, predict the products and determine if substitution, elimination, or both will occur for chlorocyclohexane plus NaOCH3 in methanol. So the first thing we do is draw the molecule, and this is the molecule. It's a cyclohexane ring with a chlorine attached. In NaOCH3 and CH3OH, well, we ask ourselves what kind of a substrate we have. We have a secondary substrate. It's a second degree. And we have a strong base and nucleophile, unhindered. Because it's a secondary substrate, these are the most difficult to predict. They're equally likely to go through SN2 or E2. We know it's going to be second order. E1 and SN1 are not possibilities because we have a strong base. So SN2 and E2 are both going to occur, and the products will be the substitution product will just be the result of the replacement of the leaving group with the nucleophile, and OCH3 is a nucleophile. And the elimination product, there's only one alkene possible for this, and that's the elimination product. Part C asks us to decide if elimination, substitution, or both can happen for chlorocyclohexane in tert butoxide. And we already know that since they're using the same the question talks about the same substrate, we already know that it's a secondary substrate. And the base given is this bulky base, hindered bulky base. And hindered bulky bases, tert-butoxide is a poor hindered base. It's a poor nucleophile, which means SN2 is not a possibility, or it's minimized, which leads to the products which leads to that being the alkene being elimination being the major reaction, and the alkene being the major product. This was an example of how you could apply the knowledge of the conditions that are most suited for elimination for making alkenes. Please do let me know if you have any questions, if there's anything that can be clarified further.